So in this recording, we're going to talk about what some of the mathematical models are for phenomenological forces. And so to do that, what I'd like to do is sort of think about a table. And in that table, we'll first list what type of force we're talking about. We'll give an example of when that force applies. And then, since we're talking about forces, forces are vector quantities, right? And so they have both a magnitude and a direction. So we'll talk about what the mathematical model is for the magnitude of the phenomenological force, and also what the mathematical model is for the direction of the phenomenological force. And I think in this clip we'll probably end up just talking about friction, because friction is one that is relatively challenging to get right. So let's start by talking about static friction. Okay. Obviously, an example of static friction is that you've got some object that's sitting on some other surface. You are pushing against that object. That's a person pushing, but the object is not moving. That is, the object, there's enough static friction that you actually can't budge the object with the amount of force that you're applying. So if you imagine having some huge crate sitting on the ground and you're pushing against it and you can't get it to budge, the force that is keeping it from budging is the static frictional force. Okay. Well, we can think about direction pretty easily in this. If I'm pushing on this object in some direction f sub t, where f sub t means the sort of force that's tangential to the surface, the direction that the frictional force acts is opposite whatever force I am applying. So the frictional force is first of all tangential to the surface, and it opposes the other applied tangential forces. So we could sort of write that as minus t hat to indicate that it is tangential to the surface and it is opposite the direction of the other applied forces. So that's not the greatest notation, but you can get the idea here that in this case, if I'm applying a force in this direction, t hat would be in that direction, and minus t hat, the direction of the frictional force, would be opposite that. Okay. The magnitude of the static frictional force is actually challenging because it's whatever it needs to be up until some maximum value. So it's actually equal to the other applied forces so long as the magnitude of that total applied those total applied other forces is less than or equal to what's called the static coefficient of friction times the normal force. And obviously we've not talked about the normal force yet, but I expect you've seen the sort of idea of the normal force before. The normal force is however hard the surface is pushing back up on the object in order to keep the object from falling through the floor. Okay, so what that means is you can't ever actually tell what the static frictional force is without knowing what other forces are being applied to the system. Okay, it is not the case that the static frictional force is equal to mu sub s times n unless it happens that you are pushing on the object with a force of exactly mu sub s times n. Okay. In contrast, and so to that extent, notice that this is actually what you would call a constraint force. That is, it is a force that keeps the object from moving, and it's whatever it needs to be to keep the object from moving up to some maximum value. Okay. In contrast, we can think about kinetic friction. Right? Kinetic friction is sort of the same situation, except for now that crate has started to move. Right? So it's moving, and you're continuing to apply some force to it, right, with my very, very long arms. And so that's the static frictional force is the force that's opposing that motion. And again, it's due to this idea that you're breaking bonds at the surface and and thereby taking some of the work that you're doing, pushing the object and turning that into thermal energy. From a magnitude perspective, the kinetic frictional force is much easier to talk about. It's simply what we call the kinetic coefficient of friction. So the coefficient of kinetic friction times the normal force. And again, the direction is actually a little bit different from what the direction is for the static frictional force. For the static frictional force, the direction is determined by what direction you're pushing on it, right? If you're pushing on it in the I-hat direction, the static frictional force is in the negative I-hat direction. In the case of kinetic friction, the direction actually is in the minus V-hat direction, right? So whatever direction the object is moving, the kinetic frictional force is opposite that motion. So it tends to slow down the motion. And I think we'll stop this one here, and then we'll talk about some of the other phenomenological forces in the next